next talk is going to be given by Professor Juan Bisquert. Professor Bisquert is a professor at Applied Physics in the University of Jaume I in De Castillo in Spain, and is the director of the Advanced Material in the same university. He was doing a very interesting work related first on the sensitized solar cells, organic solar cells, and now on perovskite solar cell. And today he's going to speak about operation and recombination in perovskite solar cells.
Thank you very much for the introduction. Thank you very much the organizers, especially Monica, for inviting me. And what I'm going to talk, if I can, some advances in the understanding of the device operation of the perovskite solar cell, rather than more fundamental semiconductor properties. So what happens when it works? There is a big protagonism of the ionic motion, which is complicating a lot the operation of the device. This is a striking phenomena with the planar configuration, all right, with the contacts put on top of a film. Then when you put voltage, and you're having photoluminescence, but a black region will grow quite slowly. You can see with the microscope, and it's with a moving front, which is sharp, all right? So this, we believe, is an effect of the ionic defects traveling and darkening the sample, but we don't have a model yet, but we hope to have one soon. And this is very much correlated with what happens on the interface, what happens in the bulk. Then we need to understand, have more insight, and we use the capacitance for that. We see a capacitance growing with voltage, and we see a capacitance changing with time, giving us information about accumulation at the interface. So what will ions do? Now I am not on a planar mode. This is a diode structure like the solar cell because it has two selective contacts. And then in the normal solar cell, you will inject or extract electrons and holes at the two electrodes. But here you will induce also ion drift. Okay, so then you have simultaneous ion and electronic motion, and this is called a mixed ion electronic conductor. And it's quite difficult to study because whenever you put voltage, you induce, in principle, 4 types of carriers, like the positive and negative, electronic and ionic. So it's quite complex to distinguish which they are. The second thing is that you will modify the operation of the sample because of surface polarization and probably changing surface recombination, etc. The first thing we want to do is to have an energy diagram, so we started doing some simulation work because it's not straightforward to see how the 4 carriers will be distributed. Then in principle, you could have just this standard model where you have equilibration of the 2 contacts and an electric field inside, but you can also have then ion drift polarizing and cancelling internal fields, for example. This is one possibility, and there are many. You can do lots of different models according to assumptions, and the interesting thing is to know which is the right one, okay? So this is work done with Pilar Lopez. She's here, and we'll talk later also. She's doing these nice simulations because we want to know the distribution of ions, for example. It's quite important because this will control the Schottky barriers, the electrostatics, and then the energy diagram. Okay, this is something we want to know in more detail, and this is advancing. And for example, this is something a little bit obvious when you know it, but if the mobile ionic density exceeds the intrinsic doping density, then you will be controlled by voltage. You can invert the Schottky barrier from here to the other side, because these moving ions can control the depletion layers, so it will be extremely complex. Okay, this is something we can imagine. As I said before, we are very interested in making electrical measurements such as the capacitance, and this is something very classical, for example, from polymers or whatever system you want, is that the capacitance, when you measure with respect to frequency, you'll have different steps because each capacitive process has also a relaxation process, and when you move with a frequency higher than the relaxation, you lose this polarization mechanism. So it goes in steps, and this is something that my colleague Germán García Belmonte. He's the protagonist of clarifying the interpretation of capacitance in perovskite solar cell. I will talk a lot about this today. This step here, you see there's something big at low frequency and something more flat, but going down in temperature, you can move the relaxation time in this direction to slower so that you can see different polarization phenomena. And he also measured the dependence on thickness. So we got this very important picture, which is a big polarization at low frequency, which is interfacial, and a plateau at higher frequency. This is the electric polarization of the perovskite, okay? And now later on, we have a very stable observation of the dielectric polarization, and this is changing according to conditions. For example, if you put organic contacts, this goes down dramatically. You see, it will not rise. It will rise at very much lower frequencies, but not here. So that this is shown to be interfacial. What is this big capacitance? Here in the dark, we go up to 10 microfarads per centimeter square. This is typical Helmholtz capacitance from electrochemistry, because this is an solid-state electrochemical system, because the ions are moving over there. So you get polarization of ions at the interface, and this is well explained by the typical Helmholtz capacitance showing due to the ions motion. Now, when you have some capacitor in the system, in your transient experiments, you will have charging and discharging of the capacitance. And this immediately gives rise to hysteresis. If you have a big capacitor and move your voltage step fast, then you cannot reach equilibrium at every step. You generate hysteresis, which is capacitive hysteresis. And of course, it's not the only kind of hysteresis, but this is an important one because it will interfere in any transient measurement that you want to do. Okay? This is an important discovery by Hyun Kim. She was doctorate with Nangyu Park. Nangyu, hello. Yeah. The work we did together in Seoul, so that larger hysteresis is correlated with larger capacitance when you have TiO2, and lower hysteresis when you put organic contact. So, for some reason, we don't know very well yet, titanium dioxide gives a very big capacitance, and other things give a smaller capacitance. So it will have larger capacitive hysteresis. Many people don't like it to see hysteresis in your system, so a lot of people is running away from titanium dioxide. Maybe this is not so bad, it has to be clarified. Another important contribution is by Stefan Weber, like Kelvin probe force microscopy, cutting the sample and scanning the voltage, and then you make a second derivative and you discover where is the charge accumulated. You see very flat, this is confirmed now also by experiments in China, very flat potential here, and here a lot of charge in the TiO2 contact, huge quantity of charge. Then we move to the observation of capacitance under illumination, which is critical, of course, for the photovoltaic operation. Here, this is the baseline I showed before, like this one, like 10 to the minus 5, but then under light goes 1,000 times bigger, 10 to the minus 3, okay? Now, this cannot be an ionic surface capacitance, because the ions cannot become smaller. But the electrons do not have size, they do not have limit. So that it is well known in transistors, when you go into accumulation, like this case, putting the majority carrier Fermi level into the valence band, then your capacitance can go as big as you want. Of course, in transistor, capacitance is limited by the series, oxide, insulating layers. In the perovskite, it's not limited by any series conducting, insulating, because it is conducting. So that the capacitance can go very large, and then if you analyze this, we did with Germán, Isaac, Sarasua, then there's a typical exponent 2 kT in the denominator, and this was observed for the perovskite solar cell in some conditions, not always, because it's a little bit more complex, but we get the conclusion that under illumination you get a big polarization not only of ions but also of electronic charge at the interface. So now this starts to explain the complex dynamical phenomena of the perovskite solar cell, because you are calling a lot of charge to the interface and ionic charge, and they have very different response times, because the ionic diffusion coefficient is something like 10 to the minus 12. It's quite small, so you can see you can see the time of moving ions is the same time that we live in, okay? So you can see the effect. This things go into seconds, okay? While the electronic phenomena are much faster. So when you come here, you have to do this polarization, and you are bringing and removing electronic charge, and in another time scale, the ions can respond much later. This gives you delay when you want to discharge something, and this we expressed as the surface polarization model. You build charge accumulation, but if you start to discharge fast from going from forward voltage to reverse voltage, you will get an overshoot because you free this charge at the surface, okay? So this is one famous, this overshoot has been observed since the very early samples in perovskite solar cells, and this is a capacitive effect, okay? When instead of seeing the capacitance, you see the JV curve, you see the capacitance always lies here. One type of hysteresis, of course, I repeat, there are others. This is just about only polarization. Of course, in solar cells, we have something very important, which is recombination. And here, now you can see the work with Hongwei Han in China, published last year, that by changing just one parameter of the perovskite solar cell, which is the compact TiO2 layer, we can change from the normal hysteresis to the inverted hysteresis, in which the voltage coming back grows instead of decreasing, okay? Why is this? Okay, because we're having this polarization, and this is the critical interface, not the mesoporous. If you change the compact layer, you change how the ions and holes accumulate there, and you change how they recombine. So you can play with the two factors and pass from one to the other. Okay, so this is bringing ions and holes here, electrons at the TiO2 side, and then modifying the combination, you can tune the sample behavior very well. Now we are starting for the inside of the capacitance made by my colleague Germain. Now we want to go into a full equivalent circuit, which will explain recombination, transport, etc., and which we don't have it yet. But it's very stable. We know there are, in the best samples, there are two arcs, like this one or this one. One at low frequency correlated with the large capacitance, and the other correlated with the dielectric capacitance. So that probably one could distinguish bulk and surface recombination, and then we have to clarify which possibility into these diagrams we have. But then it is not so simple, because of course the two capacitances are very well decoupled. The low frequency goes big with the voltage, and the dielectric capacitance, of course, is totally stable. But resistances are correlated of the two arcs. So somehow the two recombination processes are connected. Somehow they are the same, but this is not well understood yet. How is possible that two things geometrically different behave the same? This is, in my opinion, a key mystery of the solar cell. Okay? Of course, we can study them and see some difference. And what we did with Anders Hagfeld and Juan Pablo Correa and also Von Gastres was to measure pristine samples, and like 18% efficiency, very good efficiency at this moment. And we could see very good, by measuring the resistance, you can determine very well the diode factor in the JV curve. So this was close to 1, and the two resistances, high and low, were correlated. But when you do some scanning, some voltage, some modification, immediately this goes to 2. Very much far from ideal, all right? So that there is a big influence of the voltage via polarization. So it's not so easy to determine when, what, and are you measuring depends a lot on the history of the sample. This is critical, okay? Of course, changes in surface, and there are also changes in the bulk. For example, this is work done by Hongxia Wang in Australia, and then she put vanadium into the mesa treatment of vanadium post making the cell, and then you can recrystallize and make much bigger grains and approach ideality. So now, of course, this can be a factor of the bulk grain boundaries, but of course here you can also modify the interface with the contacts, which is playing such a big role. Okay? Another curious thing is that you get very good, this is something troubling sometimes, but it's just a dynamic phenomena, is that your capacitance becomes negative and you get, instead of getting two arcs, you get big loops here, you see. And this, we believe at this moment that this inductor, it has nothing to do with a magnetic inductor. The inductor represents some coupling of the dynamics that goes the other way around from a capacitance, is also controlled by slow dynamic effects at the contact. But this needs more work because this is indicating some dynamic process between the bulk and the extraction, and this might be important. I will end with some new results. By the material study was done by Cristina Roldan in the lab of Nasseruddin, and then they are using 3 different contacts without electron transport layer, with compact TiO2, the mesoporous, and these have a very big work function different. It's like 1 volt, okay? So everybody knows if we make this diagram, there will be a very big difference in the electrical field. And according to understanding of many people, this will change the photovoltaic correlated with the work function. Okay, so I have to announce this does not happen. There is a 1 volt difference in work function, but the voltage is the same, and these are all quite good solar cells. So it's nothing defective, nothing suspicious. It's just that the photovoltaic in a perovskite solar cell does not correlate with the work function of the contacts. All right. There are differences of hysteresis because there are big differences of capacitance. As I said before, the capacitance is very critically, it's an interfacial phenomena, this low frequency capacitance. So it's critically connected with the structure of the interface. But this does not affect the performance so deeply. So this is something now we need to understand. In conclusion, we have a very good understanding of properties of the capacitance. This gives us a lot of information. This is the bulk sample, so we can correlate with bulk phenomena here. Lower frequency, we have polarization, but it's not only the ionic polarization. Under light, you start to flow, you bring positive, negative electronic, you induce more recombination, and in the end, the samples up to 18%, more or less, I think they are controlled by surface recombination. When you go higher, this has to be removed because this is not necessary according to the fundamental principles of recombination, and it's critical to recognize this. And then still, we do not have a full understanding of the equivalent circuit. Okay? And now we published a review paper on the things we know so far. I'm very grateful to the workers like Pilar López Varo and Sandeep and Germacia and Osbel Almora. And finally, I want to announce that I finished my series of books, which is books on solar cells about the hybrid and organic solar cells, which ones know. Okay, in a structured energy device 4 years ago. Then last year I finished Foundation of Carrier Transport and the book about the hybrid and organic solar cells. Okay, so if you believe that solar cells are controlled by junction, you can read this book, which is written to bring the news to the world that it is not. Thank you.
Yeah. Thank you, Juan. Actually, in your first the slide, you show that the some two electrode, positive and negative electrode bias on the bias voltage electric field. You show the some disappear of the PL intensity, which means that the probably iodide will accumulate at positive electrode, negative ion. What's going on about the some after removal of the electric field, and then stored some ambient condition or some other the condition, and then measure again, you can see some the recover of PL intensity.
That's right. Yes, yes. It's you can displace the ions, so it has a velocity of like micrometers per second, and then you can invert it back, or you can leave it alone and it will recover. So it's totally a transient phenomena because you are displacing like the ionic defects. They affect the luminescence somehow. It's not clear how. So this is open for discussion.
Well, thanks a lot for this nice review of what you have done, which is very important to understand, I mean, this hysteresis. I mean, you show that inverted is not affected by the hysteresis. I mean, whatever you use, I mean, use also inorganic nickel oxide, I mean, and it's not hysteresis. Which is the main difference, I mean, between the normal and the inverted? Why in the normal you have a lot of hysteresis, if you have mesoporous, planar, whatever, large hysteresis. In the other one, you do not have hysteresis. Why? I mean, in simple words.
In simple words is that I don't know. But I can speculate about these questions comes up always, of course. Must be about the structure of the interface, because this polarization occurs in 2 nanometers. So must be about how the hybrid perovskite meets TiO2 or meets PCBM, because if you change that, you change a lot the polarization, hysteresis, etc. But there is a need also of studies that go to this place while the sample is in operation, and this is not easy. It's not easy. You can do it with all the army you have in Rome. Okay. Sorry not to be a better answer, but it's quite challenging here.
Thank you very much for your talk. I would like to ask you about the mechanisms between electrons and ions at low frequencies. Can you explain it more carefully? What's happening between ions and electrons at low frequencies?
Between ions and electrons don't happen anything. They don't like each other. So there's no reaction. But what we can measure here is something electrostatic, because you bring electrons, when you put voltage, you bring more electrons to the surface, like here. You bring holes to here, creating accumulation, you bring electrons. So these ions are called by electrostatic reasons. Okay? This is just electrostatic. Another thing is that at the OMTAT side, for example, then ions can go into there and make an electrochemical reaction, and this can happen also. And this is very bad because you can modify the conductivity of the OMTAT. You can degrade the interface. You can do a lot of things. Okay, but in principle, I talked only about the electrostatic effect that affects how the solar cell works. So it's just by charge compensation, because when you put VOC, you are bringing charges, electronic charges. They call the other ones, but then the other ones are more slow. They cannot go away, so that they hold the polarization, and this is associated to low frequency effects.
So maybe the last question, because we have to.
Hi, nice talk. Thank you very much. I would like to ask you about these new approaches between two-dimensional and bulk three-dimensional perovskites that has been published recently with improved stability. They may lead to very interesting capacitive effects between the 2 kinds of structures. Have you done some work on this issue?
Not yet, because it's difficult to see internal. You can see it somehow. If you have grain boundaries, you can see polarization at grain boundaries. This is feasible, but we haven't done yet because we don't have the standard to make these samples nicely. But it's quite interesting.
So thank you very much. Again, so let's thank again.